SwayamPrabha. Digital India. Educated India.
So welcome to lecture number 23 of the Statistical Thermodynamics course for engineers. Now, our analysis of the diatomic molecule, as we said earlier, has led to very important expressions for the allowed energy levels and the degeneracies, which is what is important for the stat perspective. Now we begin that how about taking the electronic energy mode? And if we take a prototypical system like hydrogen atom, this is a little easier because hydrogen has got a proton and an electron. And as a matter of fact, this is almost, we can replicate a very similar analysis like we did for the diatomic counterpart, because now it is also a two-particle system. It's a two-body analysis. So again, we can separate the external and the internal energy modes, okay, by using the center of mass concept and the relative coordinate system. Except here, the only viable internal energy mode arises out of the electronic structure of the hydrogen atom. Okay, so what we do now, if you go through the motion, that electronic mode, which is given as r theta phi, again can be split into two parts, r y theta comma phi. Okay, such that once we have done this, we can also now revisit the same equation that we did earlier. Okay, so which is basically, let me just recopy the equation over here so that it is easier for everybody to understand. Okay, so if we look at, this was the parent equation, if you recall. Okay, r squared r by plus, we brought in the concept of the reduced mass square internal minus VR, okay, minus alpha into r is equal to 0. So this was the r equation. This equation now can be reduced in a similar form. So just we can replicate the similar form. So this kind of becomes d by dr square d by dr is e mu r square by h bar square d electronic minus VR, okay, minus alpha into r equal to 0. So here, of course, the spherical harmonics y I still hold in and directions. All right, in theta and phi directions. So what will happen is that we obtain an analogous solution for y. So that solution, analogous. So what we did for the diatomic particles, so analogous solution becomes yml theta comma phi is equal to 2l plus 1 l minus mod m factorial divided by 4 pi L plus modulus of m factorial. This whole thing is raised to the power of half e mod m L cos theta EIMI. So this is the analogous solution. Okay, and similarly, alpha is equal to L into L plus 1, where L is greater than or equal to the mod of N. So similarly, we introduce the concept of orbital angular momentum by invoking the equations that we did earlier. I will again recopy the equation. If you recall that L square is L hat square was given as J into J plus 1 into H square bar. Recall this was from the diatomic counterpart. So invoking similar type of equation here, now it will be L square L into L plus 1 into H bar square. So it's very similar. Okay, and we recall that the magnetic quantum number M can take 12 plus 1 possible values. Okay, given by M equal to 0, plus minus 1, plus minus 2, continued up to plus minus L. So this was, if you recall, this also we did it. Okay, so if you recall equation, I mean from the book it is 6.56. So that equation you can replicate. Okay, so again, by using the previous forms, okay, once again, if you recall that we did defined Lz equal to mh, if you recall, this is what we did. Okay, that the z component of the angular momentum, So this led to the quantization along the z-axis, if you recall. Okay. But this time for atomic hydrogen. So this time it is the same thing now for atomic hydrogen, that we define the z component of the angular momentum, and that is quantized in that particular way. Okay. So based on the above development, the distinctive mathematical feature for atomic hydrogen as compared to diatomic molecule is the radial component of the Schrodinger's wave equation. So let us look at the radial component of the Schrodinger's wave equation and see what is new, because up to this point it is more or less the same. This is almost analogous, this is absolutely analogous, this is also analogous, and the quantization along the z-axis is also similar. So there is no difference between this and a diatomic molecule at this particular point. Okay, but the distinctive feature comes from the radial component. So if we write it, the distinctive feature, okay, for atomic hydrogen, okay, as compared to diatomic molecules, okay, is the radial component. The radial component of Schrödinger wave equation. Okay. So what was that? It is d by dr square capital dr minus L into L plus 1, right, divided by r square minus 2 mu by h bar square the electronic energy plus E square 4 pi rho is equal to 0. The expression. Okay. So this expression you can also, if you revisit the previous chapter, essentially find. Let's quickly copy this for you. That if you recall, the VE was equal to minus E square 4 pi epsilon into R. This is what has been used over here. Okay, that is the potential energy. Okay, because that was the electronic potential energy. Okay, so now, so this is a complicated expression. Now you can do a few transformations of this equation, and we are not going to go into the details, but we are going to define a few variables which will kind of make this equation a little bit easier to deal with. Let us define rho is not density. It's 2r by n a naught. Okay, then we define n square is equal to minus h bar square 2 mu a naught square by the electronic energy, and a naught finally is given as this mu square. Okay, so these are the three variables we define, and then we use these variables here and transform this equation. How do we transform this equation? This equation now becomes 1 over rho square d by d rho square d by minus L into L plus 1 rho square minus n by rho plus 1/4 into R is equal to 0. So this is after a few transformations when you use these variables here, and then this equation kind of reduces to something like this. It reduces to something like this. Okay? It reduces to something like this. Okay? So now what we can do is that we can use the usual power series approach. This approach to solve this. To solve this. Okay. The normalized solution becomes n is equal to minus. Okay. This is a long expression once again. L minus 1 factorial divided by 2n into n plus 1. Okay. N plus 1 factorial. This is raised to the power of 3. And then this entire thing is raised to the power. In the second term, a 2n a naught raised to the power of 3 by 2. Then you have rho L exponential minus rho by 2 L 2L plus 1 N plus L. Okay. Where, so this is a solution where L 2L plus 1 N plus L rho is equal to summation A equal to 0 N minus L minus 1 minus 1 A plus 1 So n plus L factorial square divided by n minus L minus 1 minus k factorial 2L plus 1 plus k factorial and k factorial. Okay, and this raised to the power of k. Okay, this is called, this L is called the Laguerre polynomial. So this is called a Laguerre polynomial. Laguerre polynomial. The continuity of this polynomial, continuity of the polynomial demands that principal quantum number n, okay, n, obey n equal to 1, 2, to L, which is less than n. So that L is equal to 0, 1, 2, n. So this is what the Laguerre, this is given by the Laguerre polynomial, as we said. Okay, and the continuity of the polynomial demands that the principal quantum number obey this set of rules. Okay, so now let us look at the table. Okay, so that we can, first associated the Laguerre polynomial and the radial functions can be given as. So this is the radial function. Okay? The radial function. So n equal to say 1, L equal to 0, L, which is the Laguerre polynomial, 1, 1 rho is equal to minus 1, and R 1, 0, okay, is given as 1 over A naught, okay, 3 by 2 into 2 exponential minus R by A naught. Okay, that's the first one. So if we make a table like this, and then n equal to 2, L equal to 0, L to 1 rho equal to minus 2 factorial 2 minus rho. Okay, and R to 0 is given as 1 over 2 A naught raised to the power of 3 by 2 into 2 1 minus R by 2 A naught exponential minus by 2 A naught. Okay, so this is the first one. This is the second one. Similarly, I'm just writing one more. So n equal to 2, L equal to 1. Okay. So L 3, 3 rho equal to minus 3 factorial. Okay, and it is given as R21, which is basically equal to, again, 1 over 2 A naught 3 by 2 into 2 1 minus 2R 3 A naught plus 2/3 3R by 3 A naught square, and exponential minus 3R by 3 A naught. So long and so forth. You can compile all these numbers. It is also given in the book. which is table 6.3. Okay. So you have, what we have done is that we have compiled the Laguerre polynomial and the corresponding radial function in this particular way. Okay. This is the first few radial. You can compile up to a lot of these numbers. Okay. As expected, that each tabulated radial function has been normalized by integrating with respect to the radial portion of the differential equation. So this is to assure RNL star into RNL R squared dr is equal to 1, okay, because your d tau equal to R squared sine theta dr d theta d phi. Okay. So the probability density function associated with table 6 point, the table that we just now presented, is also shown in the figure in the book, which is 6.4. Urge you to take a look at it. Okay, so but I will just compile a few. I will try to draw a few, okay, for the sake of understanding. So this is say 0. This is say 5, 0.1, 2, 0.3, 0.4, 5. So this function is something like this. Peaks pretty early and then it decays like this. So we see, so this is chi 100. So we can, on the other hand, just to reiterate, the chi NLM, okay, R theta phi is actually therefore written as RNL rho, okay, multiplied by YML theta comma phi. This was the total solution, right? So this is basically with respect to n equal to 1, L equal to 0, n equal to 0. Okay, so that is the first, cloud. Now similarly, we can draw a second one, just to give a pictorial feel of the whole thing. Say 0.1, 0.2. Okay, so this is chi 200. Okay, so this has got a smaller peak, this, and then and trembled a little bit. So like this. Peaks and goes like this. Okay. So this is chi 200, and then you write it the second one with 0, say 5, 10, 15, stuff like that. This is chi 210, say. Okay, so this peaks around 5, is like this. So that is one. And then if you go on further, you can go on doing this basically. So that chi 300 will equal to this, something like that. Okay, 300. Now you can do 310 and so on and so forth. Okay, so if the orbital angular momentum, now if the orbital angular momentum L is equal to 0, okay, the most probable okay, locations are depicted as we saw. So these are the most probable locations. Okay. So this is the most probable locations is suggested, and they actually are as shown in the figure, basically shown in figure above and also in the book. Okay. Now this has got a particular charm, this duplicates, this kind of replicates, duplicates, this kind of duplicates, okay, the basic spectral features of the, so it duplicates the electronic orbits, and also the special features, of the features of the basic spectrum, spectrum as suggested by the Bohr model. But obviously this adds more value, because now you can see that how the wave functions will look like for different types of quantum numbers. So that is a very interesting and so it adds value to the basic model that was suggested by Niels Bohr. Okay, so in other words, also we can see that if you look at the figures, that you can see the electron cloud can be very radially stretched. Okay, it can be found in multiple radial locations as well, right? It's like a wide zone that is presented over there. So the permitted spatial distribution is much more complicated, but at the same time one can see that using these features that we have outlined over here, you can predict that how the basic electron cloud is going to perhaps look like. Okay, so from the perspective of stat thermo, we now are able to get an idea about the energies and the degeneracies, the allowable energies and the degeneracies. So the electronic energy is Hc minus E4 8 E0 squared CH cube into 1 over n squared. Okay, so this is different from Bohr, except that we have used the reduced parts. So that is the difference with Niels Bohr. And this enables us to calculate the Rydberg constant, if you remember. So Rydberg constant, when it's calculated from this, is 109,683 centimeter inverse, which is very close to its experimentally measured value. So we recognize that in addition to equations, these two equations that you see over here, we have now developed a more robust model from the Schrödinger's wave equation, and then hence it can be applied to more complicated molecules and atoms, because it explains the Bohr spectrum and more. Okay, when you look at the probability distribution, okay, for these different types of things. Okay, here of course what I forgot to write over here, the axes are basically given as sigma square divided by A0 into R NL squared into sigma. Okay, so this is basically the radial function. Sigma is basically R by A0. Okay, so it is some kind of a dimensionless probability function associated with the radial portion of the wave function. Okay, dimensionless probability distribution function. Okay, so this is what we have plotted here, okay, with respect to the associated with the radial portion, okay, which is sigma equal to R by A0. Okay, so this is what has been plotted, okay, with respect to the dimensionless radius, so to say. Okay, so in other words, this axis is sigma square A0 R NL squared into sigma, whereas the x-axis is basically sigma equal to R by A0. It's like a dimensionless radius, and this is the dimensionless PDF. Dimensionless PDF. Okay, so this is a dimensionless PDF associated with the radial portion of various wave functions. Radial portion of it. So this allows you to measure the extent of the electronic cloud spread, or the probability of that, what is the zone that the electronic cloud may be available. So that is what it is what it is shown in this particular figure. Okay, so, and we have also know that now the Rydberg constant is pretty robust, and this is how we have calculated the electronic energy levels also. Okay, so next class we are going to do a sample problem and then move on and see what else is there in store for us. Okay, so see you till next class.